Adjacency list representation of graph. Adjacency list representation is a way of representing a graph in which graph is represented as a collection of linked lists. So what we'll have here is we'll have an array. This array will be array of pointers, and each of the pointers, they will be pointing to linked lists. So this is how we are going to implement. Similar to what we did in the last lecture, we'll first draw a graph, and from there we'll try to construct adjacency list. So we'll take the same graph that we used in the last lecture. The purpose is I want you to clearly relate what difference will it make when I represent using adjacency matrix and adjacency list. So we'll take the same graph and see both the representations. A, B, C and D. These are the vertices. First thing is, there are 4 vertices. Whatever be the number of vertices in your graph, that should be the size of your array. So I told you should have an array of pointers. So this array will have a total of 4 pointers inside because you are having 4 vertices. So each of the entries in this array, they will correspond to vertices in your graph. So first entry is corresponding to A, second is corresponding to B, third is C, and fourth is corresponding to D. So corresponding to each of those vertices, you have a pointer in this array. So all these are pointers. See, it will point like this. Each of these are having pointer inside. Okay. What is the next step? Whenever you see that there is an edge starting from this vertex, you'll add that edge as a new node in this linked list. So for example, in this case, you have an edge from A to B. So from vertex A, there is a link to vertex B. This will be represented as a node in the linked list. So you will have a node with value B. This will be appended to this linked list. Next thing, from A, there is an edge to D as well, which means not only B, you should also have D here. So it should also have D. D is also part of your list. So from A, you have only 2 edges, both are covered. So you are done with A. Next, you will go to B. What will you do in B? In B also, you see with what all are the edges. From B, there is an edge to A and there is an edge to D. So you should have A here and also D here. Next thing is, you will go to C. So one point to note here is, if you have an edge from A to B, that also means you have an edge from B to A because this is an undirected graph. So corresponding to every edge, there will be 2 entries in total in this adjacency list because one is an entry in A corresponding to AB. So that is this entry. And second is an entry in B corresponding to BA because both are present as it is an undirected graph. So from B there are 2, we covered both. From C there is only one edge which is D. So to D we are having an edge from C. And from D we are having 3 edges. It is going to A, B and C. So from D you should have to A, B and C. So this is the representation of this graph using adjacency list. Next thing is, we presently considered unweighted graph. What if it is a weighted graph? In that case, previously what we did in case of adjacency matrix, what we did is instead of putting the value 1, we put the value of weight. Whatever be the corresponding weight, we put that value. But here, you are adding a new node with the name of vertex. So in this case, there is no concept of 1 and zeros. So what will you do here? Here if you have to add weight, let us say AB is having some weight 3, then in this node, instead of simply putting B, you have to put B3. So you should put it as pairs. So instead of single entry, you will have pair entries. For example, B3, and instead of this D, let us say if AD is having weight 2, then you will be having D2. This pair will be inserted in this node instead of simply inserting D. This is how you handle weighted graph in case of adjacency list representation. Next thing is, what about directed and undirected? So if it is undirected, we already saw that whenever there is an edge from U to V, that is from somewhere, like from A to C, then you should have one entry in A corresponding to AC and one entry in C corresponding to CA. Because it is undirected, both sides the edge would work. But if it is directed, then you only have to add edge in one end. So if this is, let us say, directed A to B, then in BA you can't add an edge because only AB is the edge if it is directed. And next thing is, what did we say in the last lecture about matrix? What were the advantages of matrix? Main advantage was that we had an order of one axis whenever you wanted to look for any particular node. That is, whether you want, if you want to check whether an edge exists between any two vertices, you could have directly found it out in order of 1 in case of adjacency matrix. But in case of adjacency list, there is a problem. The problem is, this time you can't directly go and check somewhere. If I ask you that go and find whether there is an edge AB or not. If you go to A, you can't directly say whether there is edge AB or not because there is a complete list that is attached to A. So here the problem is, you may have to go through this complete list in order to verify whether one particular edge is present or not. So this verification, what could be the worst time it can take? So this will take order of degree. So what is the degree? Degree is the maximum number of vertices to which any vertex in this graph is attached to. For example, in this graph, D is attached to 3 different vertices. So degree is 3. So whatever be the degree of your graph, accordingly your time will also increase, because in worst case what can happen? You may have to check those many nodes in a list, because if I am asking you to check whether DC is present or not, then what will you do? You will first go to the array. So accessing D is straightforward because it is array, you can directly access. See, in this lecture as well as in previous lecture, I used ABCD for understanding. So actually array indices will be 0, 1, 2, 3, 4. So you just have to map accordingly. 0 will be corresponding to A, 1 will be corresponding to B, and so on. I used ABCD so that it's easy to understand here. Okay. So D will be directly accessible because it is an array. But after you reach D, this is a linked list. So linked list do not have direct indexed access. What will you do now? You have to go through each element in the linked list and check whether that is the element you are searching for or not. So if you want to search for DC, you have to check in A, you know it is not. Then you will check in this B, then you will reach C. Then you know in D there is a link to C, which means edge DC is present. So this will take order of D time. In case of adjacency matrix, it used to take only order of 1. So that time increased to order of D, where D is degree. Next thing is, this is the disadvantage. So we are using this, means there should be some advantage that this particular representation will give over the adjacency matrix. So what is that advantage? The advantage is efficiency in terms of space, because in case of adjacency matrix, what happened is always you were using V cross V matrix. So when it is V by V matrix, order of V square space is used irrespective of the number of edges in your graph. So always you were using order of V square space. So if you are having, let us say, 1000 edges, 1000 vertices and only 10 edges, still you will be using 1000 by 1000 matrix. So that's a lot of space wasted. In this case, you will use space only if there is an edge, because if there is no edge, you won't even create a node in that linked list. So node is created only if there is an edge. That means space usage is effective in case of adjacency list. So what is the worst case space that will be used? Worst case, for this array, what will be the space used? Order of edges. So order of vertices. Whatever be the number of vertices, that many pointers will be present in this array. Next thing is, what is the maximum number of space that can be used for these lists? So if you see, you will think in each of the list there can be a maximum of order of V. So there are such order of v entries in this array, which should mean it should be order of v square itself, right? But this is wrong. It is not the case, because even though you may feel like in each of these you can have order of v entries, the reality is total number of nodes that you have here will be order of e, because whatever be your number of edges, for each edge you will have two entries if it is a undirected graph, only one entry for each edge if it is a directed graph. So total count of all these nodes will be order of e only. It won't be order of v. So whatever be the number of edges, correspondingly you will have this total number of nodes. So order of v is the total for array and order of e is for nodes. So total is whichever is larger, v or e. So order of v plus e, which means order of vertices plus edges. So whichever is the larger number, that will be order in case of space. So in terms of space, adjacency list is better, especially if you are having a sparse graph. See, if it is a dense graph, go for adjacency matrix only. You know, anyway, almost complete will be filled up. The order of v square will be required. But in case, that is, if e is order of v square, that is, if e is order of v square, automatically this will also take order of v square. So if your graph is very dense, there are a lot of edges, then you go for adjacency matrix representation only. But if your graph is sparse, there are very less edges in your graph, then you can go for adjacency list representation.